me give you a little introduction. My name's Pete Wilson. I work for Microstrip Technologies. I'm based out of Roseville, California, which is near Sacramento. And I've been doing RF PC board design for, I don't know, maybe 15 years. It takes 10 years to get to the point where you're dangerous. So I've been doing that. I do a lot of customer support. I'm an applications engineer. So when you file a support ticket with Microchip, if my first tier minions can't tackle it, they hand it to me, and I'm the one that ends up having to debug all the heavy duty problems and stuff. So what I wanted to go over today was a presentation on how to do RF modules. Microchip is pushing RF modules. They're a good thing, but people make a lot of common mistakes when they're doing a layout with them. And I've got some things with Altium that are going to be helpful. So without much ado, let's kick it off. Is this going to work? Is it going to work here? Come on. There we are. Okay. So that's the abstract. You guys probably have read all this. So a couple of things here is we're just going to try and highlight good practices. We want to gear towards newcomers to RF. And I don't want to have a bunch of scary math in here because that is usually kind of circumvents the reality of what's going on, and people need to have more concrete explanations, I feel. Let's see, these are some of the topics we're going to cover today. We did an outline of the presentation before we kicked it off. We're going to, you guys have probably already seen this, so we're just going to move on. Okay, so the first question is, why would you use an RF module? There's a number of reasons. One of the best reasons is there's lower regulatory costs in North America. In North America, FCC has this concept that's called modularly approved products, and these products require only parts A and B of FCC 15247 to pass. Certification may be reused, so once you buy a modularly approved product, or you make your own modularly approved product, you can reuse it without doing the part C of the FCC cert. For a device design that doesn't have modular approval, you have to do this additional part C, which is intentional radiation, and that's about a $10,000. Yes?
Are your slot registration going to be available after?
I hope so.
Okay.
I hope so. It better be. If not, you can come see me. I'll be at the Microchip booth for a while. So the big difference here is this is roughly a $10,000 difference in price for certification. If you're going to do an RF design, I think you need to have a war chest of about $50,000 because you have to go through the layout, you've got to do through the regulatory approval, you have to go through testing, and there's a whole bunch of back-end stuff in NRE that are important. When you use a module, it cuts all that out, and so when you go to your bean counters that are trying to assess the value of the project, you need the layout. Engineering's not free, and this is what it's going to take in order to get your $6 bag of parts through certification. If you buy a $13 module, you're almost there. The other thing is we've got low risk. We know things are going to work the first time right out of the box. You don't have to worry about doing a bad layout with RF. I do a lot of RF board chip down board layout, and it can be very troublesome and time consuming to do it. Modules much faster to market. I think the break-even point is somewhere over 10,000 units. Kind of depends on your business structure. If you're going to be doing 2 million units out of the chute, if you're Netgear, then yeah, you need to be going chip down. But if you're not, if you're going to do 10,000 units over the first year, start with a module. Get your business plan working, get your product dialed in, and then you can go into doing chip down. All right, let's keep going. Typical module features. Module will always have an FCC ID number. Let me ask this, how many people are from Europe in here? One? Okay, I'm sorry, you're in a minority. We can talk about Etsy later. So a module will usually have an FCC ID number. Ask your vendor for this. Say, hey, I want to see the FCC ID number on this module because that's a telltale to whether it's got modular approval or it doesn't. There are a lot of people that sell modules that are not approved. Also, we'll have a metal shield on it. All modularly approved products have metal shields for traditional reasons, but it's there. You can always see it. They also have internal power filtering. It may be minimal. It just may be passives. It may be an LC filter, but there's always something. You have a couple different antenna options, and we're going to kind of go into this. A lot of times you'll have a 50 ohm pin, you'll have a 50 ohm coax jack. Sometimes we'll have onboard antennas, they'll have a chipboard antenna or a PCB antenna. So those are the types of things you're going to see on modules. Here are some examples of modules, okay? So the one on the end here, this is kind of the easiest one. This has got a PCB antenna on it. This squiggly line here is called a meandering F antenna. So that's got a built-on PCB antenna. This one here has a chip antenna built into it. This is a very small Bluetooth module. You notice it's got a shield. That one's got a shield. This one here has a chip antenna. And then this device here this is not a coax. This is a coax test probe point. It is not for continuous duty. So this is where you touch down if you want to test the module. It's not where you want to connect the antenna. This style of module has U.FL connectors on it. And those are used for external antennas that are going to have pigtails on them and U.FL or IPEX connectors. This has a test point on it too, which is this target here. That's where they touch down with a probe point in order to probe it in production. So a little bit different style of connector. Also notice the gender is important with the connectors. I'm not going to get into that, but this has a male connector on the module, which is legit. This has a female connector, which is not. The other type of module you're going to run into is this is one with 50 ohm pins. It just has castellated pads and the pins pop out all over the place. So of these modules, can any of you guys guess which one is not FCC approved? Which one? What color is it? Okay, good. You get a ticket. Come on. Whoever said that can have a ticket. I'm going to just leave those up here. I don't hand them out. Yeah, so yeah, you're right. The red module, I'm like, oh, there's no shield. We don't know what that is. That's not going to fly. FCC's not going to buy that. So, all right. So first thing, one of the biggest concepts I work with RF is that I just listened to Eric Bogatin's lecture about ground planes and about people that intentionally trying to make antennas. And I'm going to take a little bit of liberty with some of his concepts because I am trying to make an antenna. And so the first thing I talk about is counterpoise, the ground counterpoise. It's essential for an antenna. I like to use this model where we've got this African kalimba in this instrument where it's a thumb piano. You hit the nubs with the thumbs, they vibrate. These are quarter wave resonators, but the thing doesn't make any noise unless you've got the big box on it. Okay, and the same thing happens with antennas, is that this is a reference design for a chip antenna. There's your chip antenna. There's a little tail on it to make it look electrically longer, but it's got this huge, whacking, big ground plane that you have to have in order for it to work. Okay, so the point here is that you need both a quarter wave resonator and a counterpoise. And if you don't have the counterpoise, it's going to be the sound of one hand clapping. Okay, so you're not going to get, it's not going to get on the air very well. Okay, so that's a thing to remember. Always be cognizant of the fact that you have to have a counterpoise somewhere. Another place we run into problems is metal in the near field region will create bind spots. So you can look on Wikipedia and they talks about the near field region and the Fresnel zones and the far field region. Anything within a wavelength, that's the near field region, and it'll cause voids and nulls in the far field region, even if it's a small piece of metal. A lot of times designers will orient their board such that metal or other metallic conductors on the board are in the null of the antenna radiation pattern. So that's kind of, you're kind of putting something in the blind spot already, so that protects you. But you need to be aware of this with your module placement. So this is a design I did originally for this board. I was going to do a board that went on top of an Arduino Uno, and my first attempt was I was going to put this chip antenna in here because I thought that was kind of cool. And what I do is I do a paper mock-up and do one-to-one plot, and then I put that on top to see how it's all going to work out. And the problem is we have this big RJ48 shield box right here under my antenna, which is not good. So we decided to do something else different, and I'll show you that later. But this is the value of doing a paper mock-up. Pair of scissors and a printer. I can kind of put something together that gives me a really good 3D model and also a system integration model, a very powerful tool. Most modern designers overlook this. let's see. Module placement. In module data sheets, you will a lot of times find these diagrams on how to do placement. The best, most common shown one is this cantilever design where the antenna and the is sitting over the edge of the PCB. You'll also see them abutted to the edge. The thing that happens here is now the FR4 is thickened because instead of just having a 40 mil thick piece of FR4, now you've got that in addition to the 62 mil thick, so you've got a 100 mil thickness of FR4, which is going to change your dielectric constant a little bit. It'll detune the antenna slightly, but not a whole lot. The other one, low performer, is to put the module inboard somewhere and cut a hole in the board underneath it. This is not as good because you don't have the ability to create radiated field in this area. This is all going to be quashed by the ground plane. The thing to remember here is, above all, do not place your antenna on top of the metal ground plane. This will kill your signal. I've seen so many customers do this where they forget there's ground plane underneath there. They put it here, or they have a ground plane under there, and the signal is dead, okay? So big thing to watch out for, particularly with these PCB antennas, is that you have to make sure that you follow what the data sheet says, because some modules are characterized to have FR4 underneath the antenna, and some are characterized to be cantilevered, but none of them will work if you have metal underneath. All right. So we're going to talk a little bit about ground plane connections. And after listening to Dr. Bogota, I've never met him before, but through our careers, we've sort of come to the same conclusions on a lot of things. For RF, low impedance current return path is essential. Kirchhoff's law, all the RF currents pass through the ground plane. Okay, so if you don't have good ground plane connections, you're killing yourself right there. You don't get your signals. I use ground plane as part of my counterpoise, so I like to have a big ground plane to have a lot of reception, a lot of area for the RF field to hit, because I'm trying to collect RF field out of the air. Let's see. Another thing I'm going to show you is interconnect. I call these cartwheels. These are the vias. Those are troublemakers in my world. The other thing, if the device has a paddle, connect it to RF ground solidly. I work on many, many low power RF parts, and they have these paddles on the back of them, and people think of them as thermal pads, but if you look at the data sheets, these parts only burn a couple of microamps, or maybe a milliwatt at most. So it's not about temperature, it's about having a low inductance path back to the ground plane. Okay, return path from a counterpoise to the modules. Okay, directed and unrestricted. Okay, that's exactly what Dr. Bogatin was talking about. All right, so here's a bad design example. This is an actual design that I got, and the customer was complaining that they were getting a minus 12 dB hit. They were losing 12 dB worth of power. So the first thing I look for is look at the ground plane. I want to see that return path. Show me the ground return path. And what I see here is the Audi symbol, okay? This thing is evil, okay? You do not want this in your RF ground plane, okay? Audi symbol always means trouble. These are thermal cartwheels. People use these for thermal relief. You don't want those for RF. Those are not good. The other thing about this module is this, guess what? It's only got 2 ground return pins, okay? So this is really pretty stingy on ground return. If you look at the way the guy designed it, here's one ground return, there's the return path right there, skinny. Here's the other return path, goes through a capacitor, goes to the ground here. So these 2 skinny paths go back to ground. So he's killing himself. Half his signal, his ground path is not there. There's also a metal plate. He tried to put a metal plane on the top part, which is underneath the module. This didn't really work well, but he did try to ground it too. But it's just really not part of the equation because it's hiding under the module. The other thing I don't like about this is he's using a negative artwork. I don't like negative artwork. Okay, this was popular back in the 80s when we were still using photography equipment we don't do that anymore. Come on, we can use we have enough problem with dyslexia, so let's just get it all into one range and not have to deal with having negative ground planes. So here are the corrections that we put into this design. So the first thing we did is we put in, he added in some RF ground plane on the top layer. Okay, that's good. He also increased the thickness of these conductors. There's your pin 2 and there's your pin 13. So those are all nice and well connected into the ground plane. He got rid of the Audi symbol. It's gone. Yay. He did put in some holes here, and these are to nail down these ground planes to his lower plane, which is good. And also you can see that here, they're just direct connects into the plane. There's no more thermal relief. So these are some things that we did to correct this. This design worked fine. He got his 12 dB back, lowered his emissions, and he's good to go into production. So, well, going too far. Okay. All right. How are we doing on time? Whoa, got to go. Okay. So one of the things we want to do about here is managing multiple ground domains. So in RF, and this is kind of where I'm going to differ from Dr. Bogington, we have what's called common impedance coupling, where both RF and digital currents throw together. And we want to avoid this, okay? And this is something that he sees also with in his digital baseband world. So what we want to do is use star grounding to prevent this. So in my world, I like to use a big RF ground plane because that's my counterpoise, but I also use a digital ground return, and I connect these two using something called a net tie. Which, have anybody used net ties within Altium? Okay, great. Okay, so net ties, it took me a while to figure out how to use these guys, but this net tie will just slide right onto those two, and it'll make the connection. It'll allow me to have two domains without merging the signal names, so that way I can undo them. So the tricks to using net tie are in the device yourself. When you're in the schematic mode, you have to add in an attribute into the properties, and that is a class name of net tie. So that should be in there. And then also you have to go into the project configuration and you have to check generate component classes and check generate net classes, okay? And also when I'm in here, I uncheck the rooms, because the rooms, I don't use rooms, but some people do. So you have to remember to do this, because what will happen is when you pull this schematic into the PCB tool, if you don't do this, it will strip out the net ties and you won't have anything when you get there. So you'll see this in the notes when you get the copy of it. We also talk about transmission lines. When you're using a module with a 50 ohm pin, you're going to have a transmission line to the antenna, whatever your antenna is. And there's a couple popular ones. A lot of guys that do modules want to do a 2-layer board, so the dominant transmission line for 2-layer boards is coplanar waveguide, because you can do it on a 2-layer board. The thing about coplanar waveguide is that the trace width is very thick. Usually in this case we've got a trace width of about 35 mils and the gap is about 6. The problem is that we're getting down to the minimums that we can do with trace and space layout. So that 6 gap is probably about as small as you want to go on a gap between a line and trace. I use a tool called AppCAD. This is from the people at Woodshot, old HP guys. I know people that actually designed this tool. This is a great tool. It's free. You can get it online. Definitely worth checking out. The other option you're going to see is microstrip transmission lines. This is a microstrip layout, and you'll notice that the top layer has been pulled back from the transmission line. I use about a 4:1 ratio. Actually, let's talk about the base ratio. With microstrip, what happens is you have about a 2:1 ratio between the width and the dielectric thickness. This is always done on a 4-layer board or more layers. And we have about a 4:1 ratio here of the pullback, so that the dominant ground is really this lower strip that's running, the ground plane that's running underneath. This sets up the physical locations in the metal and the conductors so that the microstrip works properly. The advantages of microstrip are that you can use a much smaller width of transmission line. You can start using 6 mil. I like to use a 20 mil transmission line because it abuts cleanly to the 402 parts. That's one thing I like to do. But this allows you to get a little bit finer control on the routing if you have to, but you have to go up to a 4-layer board. Transmission line goals. Yeah, use short and direct transmission line. Don't use vias through your transmission. Don't make Ys or stubs. Avoid bends. If you have to use bends, use large radius curves. Okay, there you can see papers on doing chamfered bends, but the fact is that the board etching process and traces now are so small that even errors in your etching tolerance are going to affect if you use a mitered bend. So I like to use the radius curved. Differential lines. Let's see. You can choose a line width. There's a lot of reasons to choose line widths. You have to look at what you can adjust. Usually the thing you can't change is the pitch between the pins or the pin width, but everything else you can change. You can change your dielectric thickness. You can change your thickness of the transmission line as long as you use an impedance calculator and get close to it. So with that being said, one of the key things I want to drive home here is when you're using a controlled impedance transmission line, you need to work with your fab house in order to optimize your materials and dimensions. Okay, you need to call your fab engineer and say, okay, how do I do this? What materials do you have? What's going to be the lowest way to achieve a 50 ohm transmission line or lowest cost? Very important. I had the Isola rep here, and Isola is a compound that I use a lot for PCs, and so it's important. It's a whole science of how to get your impedance correct. That's not your job. Your job is to do the rough placement, do a nominal dimension, and let the PCB guys take over and do what they do best, which is dial in their process. When you do that, though, you want to get a test coupon on the same panel with the same dimensions and get a TDR test on it, and that ensures compliance. And say, okay, I want you to show me that this is compliant. It has controlled impedance to 50 ohms, plus or minus 10%. They give you the TDR on the test panel, you know it's good, okay? So that's a real big step. This is something that they do at Apple and Palm and many other the high volume vendors just to control that their PCB construction and the controlled impedance is accurate. This is our standard stack up for 4-layer. This would be used with a microstrip type design where we're using 10 mil dielectric between layer 1 and 2. The assumption is layer 1 is RF signal, layer 2 is RF ground, layer 3 is power and signal, you can put whatever you want in there, and then layer 4 is just miscellaneous signals. I like to use a 10 mil, that way I have my 2-to-1 ratio, I get a 20 mil trace I can work with. I could also do a 3 and 6, or you can do a 6 and 12. It depends on what your constraints are and how many layers you want to go to. The other thing to note here is that I use core between layer 1 and 2 and prepreg between layers 3 and 4. Core to me is a better representation of a perfect planar surface, right? Because it comes as a slab. It's like looking at a sandwich. Core is like a chunk of cheese. It's not going to change its thickness. Prepreg's like peanut butter. It's going to mush and adapt to whatever type of contours are on the bottom of the PCB or on the layer. A lot of the electrical properties happen between these two layers. So in our math models that we use, we want to have a perfect plane there. So the core is a better choice for that, I feel. So anyways, that's a little tip. 2-layer stack-ups. So I've had a lot of problems with 2 layers. You get a lot of unintentional radiation risks. I feel that you need to have copper pore on top and bottom, and Bogatin was talking about uncontrolled copper. We're going to talk a little bit how to control copper because I think that you need it in certain places. And microstrip, not a good choice for 2-layer. Coplanar waveguide is much better because the trace widths are more realistic. Or the dielectric is thin enough. So I wanted to say something about antenna matching. A lot of times you're going to run into placing a module and trying to connect it up to an antenna, and you're going to want to have a matching circuit, okay? The module may say it has a 50 ohm output, the antenna may say it has a 50 ohm output, but at the end of the day, you may actually have to have somebody come in there and rematch it. So what I do is put this pi circuit on right at the launch point to the antenna. So this would be right at the base, right at the edge of the antenna. You are probably not going to be doing the adjustment on this pi circuit. This takes some very complicated machinery, or complicated test instruments and a lot of knowledge in order to choose the right values here. Plus, it has to be done in the final enclosure that you ship the radio in. But in terms of layout, you need to provision for these. You'll probably only use 2 of these locations, but you need all 3 in order to get full mobility on the Smith chart. Okay.
Question?
Yes. Go ahead.
When you put the pi filter in, do you want to try to keep it closer to the antenna side or closer to the module side?
You want it right abutted to the antenna as close as you can. One of the things that I do for functional testing, and that's in the speaker notes here, is that in the beginning, you don't know what those values are. So put what we call a DC blocker cap in the series and don't load the shunt parts. Okay, that way it'll work. So put like 100 picofarad or a 300 picofarad part in the series location, pull off, open circuit the shunt locations, and it'll work. It'll functionally work and radiate. It may not get the maximum power transfer, but it's good enough to get things rolling with your development. Any other questions? Huh? Somebody over there and somebody over there had a good question too. Good one earlier. All right, let's get into high gear now. All right, so Altium power tools. Okay, so the things I like about Altium are I can use classes and rules to control and manage a lot of stuff. Clearances, you saw it used for net ties up there. I use a lot of Polypore. Below this is a class that I use as an example. This is called Big Metal. And one of the things that I like to do is I have direct connects on everything on the board, except for sometimes when you have 100 mil posts or you've got big things that need to have the thermal relief. So I label those components as Big Metal. So in the component definition of the schematic, I put in this component class attribute that's called Big Metal. And because I have this class, I can add things into the class that are, and here I have several different classes. I've got Big Metal, Net Tie, Transmission Line. Okay, these are some classes that I've defined. The higher, all caps are ones that I've defined. And what we do with this is we can use rules. Okay, and so we can say, my Polypore rule that I want to say anything that is in this class of Big Metal is going to have this type of connection. Okay, so it's got a different kind of connection with spokes on it. So this is where I am allowing spokes to happen, but only on selected connections. All right, so the concept here is you can put a directive in your schematic and you can add a rule to that directive and you will get control on your layout, and it's all automated. So in my schematic, I add this 50 ohm directive to my transmission lines, okay? And I have a class, this is the class name of TRX line, so I put 50 ohms as the name. Then I've defined this class, and then when I look at my rules, I can say, okay, anything that has this rule of TRX line, when I put it up to a Polypore, I'm going to put a 5 mil gap on it. And what that does is that gives me my 5 mil gap that I needed for my coplanar waveguide. So I'm doing Polypore here. This is just happening automatically. This is my transmission line, which is I think 32 mils in this case. But it automatically creates this exact gap that I want to get the perfect dimensions for my coplanar waveguide. So that's, this is a trick of the trade that we learned through hard experience, that when you start making these special rules, you have to have a default rule to cover all the other cases. So normally what I'll do is I'll take the existing default rule and then I will just enable it as the default rule. And so this is the default rule here now. So everything not in the component Big Metal is going to have a direct connect. So this way we've got our special cases covered and all the other cases are covered. So if we don't do that, Altium can do some odd things if you just don't say anything about what to do with the defaults. EMC control. So this is where I start using a lot of copper pour. On a 2-layer board, I always like to have a ground plane on top and bottom. Also note the ground planes are stitched together. They do have direct connections, and I also have a manual connection here. So I put in 4 manual vias, and then the rest are all automated. Those come in. So the thing here is we want to eliminate floating copper. We want to reduce and metal islands, and we run a deuce next. So this is what we're talking about with controlling the copper pour. Here's a picture of the board that I actually did. So if you remember before, the previous version had that chip antenna. This now just has the coplanar waveguide, and it's going to go to a direct SMA connector, and I'm going to have a vertical antenna sticking out of the board. So we're going to get on to Polypore and how to improve things. So the thing that I don't like about Polypore is that we can get necks and islands that can resonate at unwanted frequencies. Not good. So what I do is I use larger dimensions for X necks and islands. I'll put in 15,000 square mils over here and 50 mils for my neck size. That removes the necks, a lot of the little resonant flakes of metal on there. And then we'll also go in and highlight, remove dead copper. So I don't want to have just copper randomly floating on top of my board. So this is controlling the Polypore. The other thing I do is I use stitching vias. Now these are kind of like a machine gun, so if you get it right, it works, and if you don't, it makes a big mess. So there's a couple things that we can do here. I like to have 100 mil spacing. I think that's okay. Some people like tighter. We can discuss about that offline. I like tenting. It makes them look easier. You can use floating metal underneath in order to keep the stitching out of sensitive areas. Okay, so like, let's say I wanted to have my design here and avoid any kind of weird stitching going on in here that I didn't want. I could put metal on that layer 4 level to keep it out. One of the great tricks I learned from a designer is use a slightly bigger hole, like 1.8 mil instead of, or 8.1 mil instead of 8.0 mil. The Fab House is going to round 8.0 and 8.1 to the number 92 drill, but this allows you to use the select similar objects in order to select all the routing vias, or all the stitching vias. And what'll happen is if you start moving your design from one folder to another, it will lose the fact that those were a group of vias. So if you try to use the remove group tool on something that's been transferred, it's not going to know what the group was. So this is one way of keeping things separated, and it works pretty well. Let's see. The other thing I wanted to point out here, and this is where Eric Bowden and I differ in opinions, is know what your capacitors are doing. Capacitors are not created equal. So these are all 402 parts from Murata, and this is a 10 microfarad X5R, this is a 1000 picofarad cog, and this is a 10 picofarad cog. These two parts at 1 gigahertz are not capacitors. They are inductors. They are, you can look at the Bode plot, it's going up. That's not working as a capacitor, it's working as an inductor. Over here at 1 gigahertz, the 10 picofarad is working as a capacitor. So you're actually getting filtering with this. Okay, so be aware of what you're using for filtering. Personally, I like to use a combination of a large and small capacitor. The large will help with DC transient response, local current storage, but the smaller one is going to help filter out RF because the bigger capacitor, this 10 microfarad, has no filtering capability at high frequency. I like to have 2 PowerPoint tube filters on my power circuit, so I'll have an incoming ferrite bead, I'll have the big 10 microfarad and a small RF filter in order to block out, shun out RF noise. Okay, so we're going to go on the home stretch here. We're going to go into some common mistakes that people make. This is like my number one beef, is using negative images. So when I get the design, I look at this, okay? And can you tell whether there's ground plane under the antenna here or not? You don't know. If that's what your plane looks like, this is all metal. That really looks like that. That's all metal. So there's metal down there. So this is why negative images are misleading, because when you're looking at the board, you're going to say, oh, gee, that looks like it's free of metal. It's black in there. But it's a negative image. So be very wary of this. Here's another thing that's a common mistake, this Audi symbol. If you see this Audi symbol, get rid of it. Is it connected? How would it be connected? How would something here be connected by these 4 little teeny threads? I don't know. What happens when they blow up in manufacturing? This one actually was a fractal antenna. You guys know what a fractal antenna is? You know what a fractal is? Okay, so fractal is kind of a weird little thing. It's got a lot of little triangles to it, and it makes, it kind of looks, and the composite effect is like a big antenna. This one actually resonated at 10 gigahertz. And so if you looked at the spectral plot, there was a big spurs out at 10 gig because this structure is resonant at 10 gigahertz. Okay, so this is another reason why these are not helpful. This is another classic problem, undersized counterpoise. This is an engineer that's trying to do an inverted F antenna, classic antenna design. His dimensions are a little screwy. I can go off of that offline, but the big issue here is that his counterpoise is smaller than his antenna. So, I mean, it's why, I don't know. It's just not gonna work.
Can you explain?
Yes.
A little further in that?
Oh, well, so the explanation is that what you're trying to do is you're trying to build up an electric field between the resonator, this is a resonant surface, and the counterpoise, okay? And if you don't have a big counterpoise, the field is not gonna be there. It's not big enough to hold the field. The field won't condense. It needs to spread out. It wants to spread out as wide as it can. So having a big counterpoise is essentially the receiver. I sort of look at it as the counterpoise is like the ears on a dog. If you have big ears, it hears better. And you'll see that with receiving.
Okay, it looks like it's a 4-layer board.
Right.
If we were to stack up all 4 layers, do all of them count as the counterpoise?
Only the top layer, because E field can only penetrate a few microns worth of thickness on the metal. So remember that. That's a good point. Remember that, because E field can only penetrate the top surface. It doesn't go in once it hits that metal. It's all zero. Okay. It will. You do see diagrams of it building up resonance in modes across the field, but this one should have. Classically, with an inverted F antenna, this is a quarter wavelength, and we want this counterpoise here to be half a wavelength long, okay, or at least a quarter wavelength, so they're equal sizes. But this.
Would they have been better off putting the antenna on the bottom layer? Would they have been better off putting the antenna on the bottom layer?
Well, they might be able to salvage it by making a bigger board that goes on there, but this was just not something that I wouldn't even consider it. I got to keep moving here. We're running out of time. Here's another one. Negative images again. I just kind of wanted to bag on this again. This designer sent me this design. He's got like 3 boards. He's got some weird partitions here in ground returns, and I'm like, show me the metal. Where's the metal? I don't know. So if you send me a Gerber and it's got metal on it, I know Gerbers don't lie. There's a lot of nice tools for layout and artwork and stuff, but sometimes things can be suppressed, they can be invertible, they can be inverted, they can be odd colors. So we always like to look at things in a Gerber viewer because it's metal and the Gerber viewer doesn't lie about where the metal is going to be. So this is another one. This is a good example of a board that was done. So what we've done here is we've done a coplanar waveguide, okay? We've done nice easy bends, okay? Nice radius, wide radius bends, slow easy bends. We've put the pi matching circuit right out here at the antenna, so we can match this antenna right here if we have to, or we can actually trim it. There's some trim cut lines there, maybe if we want to do that. The antenna is on the edge of the PCB. It has no metal underneath it. We have a huge counterpoise here, lots of counterpoise area, so we should be able to receive things quite well and get a nice stable transmission. We have top and bottom ground planes on this one. Stitching vias are in here. I like the gold plating. I think there's some discussion about how thick the gold plating should be because there's questions about whether nickel is bad for TEM waves. That's beyond this presentation, but gold plating is certainly a good thing to have. You can also see that there are areas in here where we're devoid of stitching vias, and that's because these have traces underneath that are blocking the stitching tool from inserting vias in these areas. So you can actually manage that a little bit if you want to keep Like if you have, like in this board here, we've got some stitching vias right here that automatically got placed. So if I were to do this board over again, I would put just a piece of metal fill on the power layer to keep those from being generated by the stitching tool. Have I used what? No, I haven't. I haven't. We can talk about that offline. I think I've got about 3 minutes left. So, takeaways. RF modules are a good thing. Low NRE, rapid time to market, high success rate, okay? If you're trying to test the waters on a product, definitely worth looking into. Always think about the counterpoise. You're gonna need that in order to make your antenna work. Controlled impedance is mandatory if you have to do a module that has a transmission line on it. Check the quality of your passives. Use good quality passives. Don't go spec a Murata part or go spec a Johansson part, but then if your CM goes in and puts Uncle Chin's Lucky Capacitor Company on there in Taiwan, you might not get what you expect. So that happens. I stay away from negative imagery. I don't see any reason to do this anymore. There's actually one reason. We can talk about that offline, but stay away from it. I don't think you need it. It's a thing of the past. Take care to position the module per the data sheet. Some modules are different, like I said. Some want to be cantilevered. Some are optimized to be put down on top of FR4. And whatever you do, do not put metal under the antenna. Let's see. And the other thing is to master Polypore and stitching of vias. This will save you a lot of work and make a nice clean design for you. It's something that Altium does very well, but you have to experiment with it to make sure you're not running amok. Okay, so that is my presentation, and I've got 3 minutes left. I think we have an announcement. Were you going to announce something?
Oh, you can ask questions, we have 5 minutes.
Oh, okay. Go ahead, questions.
I know you're troubleshooting a lot of designs. I'm just wondering what percentage of design starts have problems with RF layout?
Well, usually by the time they get to me, they've got problems with RF layout. So usually it's either that or software.
It's
So
kind of hard for you to say.
it's hard in terms of percentage. It's hard for me to say. What I'm trying to do here is set it up so that people can be successful and don't have to get involved in the same common mistakes that everybody does. Yes.
In the image that you were just showing up on the screen,
Right.
go back one or two.
That one.
Right there, yeah. It appears like you've got the coplanar waveguide, but the yellow portion that's outlining the coplanar waveguide does not necessarily follow the smooth curved arcs of.
Oh, okay. All right. Hold on. So what we're seeing here is that this green stuff, this is the solder mask on top. Okay, so the entire top is all gold-plated ENIG, okay? So you're just seeing the top paint layer pulled back here. And the reason for that is some people feel that that prohibits the E-field buildup between the ground and the, because most of that's going to happen right in the short distance. So that's the reason you don't see it.
I was just noticing right at the curves, it appears like you're encroaching, the green is encroaching on the inside of the curve.
Yeah, it is. I probably could do a better to pull it off, but there's still going to be metal underneath that green. Okay, next question. You.
On the topic of passives,
Yes.
what's the importance of using something like a X5R or X7R versus like a COG or any other like type of ring with capacitor?
Okay, so my feeling is if you're doing filtering, if you're doing any type of passive filter, RC filter, RL filter, RF bypass, use the COG. Don't even think about it, okay? The X7Rs are great for small bulk capacitors, great for providing low localized charge, but I would definitely, if you're going to make a filter, if you're going to make a filter, use a good quality capacitor because the passive is part of the filter.
Is this tolerance or no?
There's a lot of things. It's self-resonance. That's what we saw back here. Let me back that up here. Whoa. Come on, back. Yeah, it's self-resonance. So this is a 0402 X5R, and you can see it's an effective capacitor up to 1 megahertz. But then after 1 megahertz, somewhere up here about 3 megahertz, it decides to become an inductor. So it's not any good anymore as a capacitor. Okay, all right, and you.
Yeah. Could
best ways to set up a probe point on your transmission line if you're trying to actually
Ooh.
do a signal?
Okay, yeah. There's a number of different techniques, and there's a number of different people that want to do things differently. So let's talk about that offline. My personal feeling is the simplest thing to do is just have a, where's my, come on, back. I'm going back, I'm going the wrong way. Okay, here's my pi filter. Okay, so if you want to probe this, just pop off the series part, put your probe in there. That's the simplest way. Okay, in the back, all the way in the back.
Do I need a 2x2 radio or not?
A 2x2 radio? What, for two antennas? Like MIMO, multi-in, multi-out? That's kind of beyond this class. There are people that like that. There's people that like diversity. That can help a lot. It depends on what you're doing. I used to work on for a company called Horizon Hobby that made remote RC airplane stuff. And they always used 2x2 on their receiver because they couldn't tell what attitude the plane would be at when it was flying. And if you lost contact with the plane, it was very expensive. So yes, there are cases where that's important. But for a module, you're probably not going to find a 2x2 antenna port on one. Okay, anything else? Let's see, you have.
All right, hopefully this is a quick question for you. So if I have a 4-layer board, and they're all ground planes, they're cut up with signals in between, do I want to use the bottom ground plane as the reference for the antenna, or the nearest ground plane? As in use signal layer 2?
Okay, no, let's get to this. Okay, if you're doing a 4-layer board, and let's get this solidly understood. Okay, layer 1 is going to be your RF signals, okay? Layer 2 is your RF ground plane. That's going to cover the entire board. All the RF activity is going to happen between these two layers, okay? Layer 4, layer 3, a lot of times we'll do a plane down here, but that's just because we want to have a similar stack up to prevent warping, okay? The RF is not going to penetrate through this layer 2. It's not going to go down here because once the RF hits that layer, it's done. It only penetrates in a couple of micro inches. The other thing you'll see, and then you can have miscellaneous signals on the back side. So I do tend to put a plane on the back side and on the top side with Polypore, but I make sure that those are all connected together. Okay. So does that answer your question?
It does, yeah. It's
okay.
Perfect the first time. I've only come across this on a design that I'm reviewing. The other thing they did was where it was the pi network. They had 2 pi networks on the same trace, the same antenna.
That's okay. That's okay. People compound filters.
One by the antenna.
Yeah. To me that's overkill, but you know it depends.
I thought so as well. And to further elaborate, they had on the pi filters, the ground reference was the bottom layer, but on the rest of the antenna trace, it was like you had here.
No, it should. One ground, one RF ground, okay? Now there's a difference between RF ground and power ground because we want to try and avoid that mixing of your digital ground return path and your RF ground return path. Okay, very important concept. If you get digital signals like high-speed buses or switching power supplies in your RF return, that's going to mix in and it's going to cause spurs out in places you don't want to have them in your radiated spectrum. The other thing is if you get digital returns going through the grounds for your crystal, the local oscillator, that'll mix right in and it'll show up in your spectral diagram, which is...
You have that trough all the way to the bottom.
Right. You want just one RF plane and only RF things get hooked up to it.
Will the RF plane, last question, will the RF plane stop if you have signals running underneath your antenna trace? Will that kind of make the antenna trace immune to...
Well, I think if you have low-speed baseband signals that have low current, that's fine, okay, to run signals under there. If you're running high current or switching power supply signals, don't go there because then you get into magnetic coupling, okay? Once you start getting high current signals, DIDT, then you get magnetic coupling, and magnetic will penetrate metal. You can't stop magnetic. Okay, you're...
I gotta wrap it up. So if you guys want to stay after and ask me